let's go ahead and do the same problem using the definition f prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a all over h. So we're going to do the same thing again using this definition. Now we're going to get the same answer. That's not going to change. It's just the process is a little different. And you'll probably learn to prefer one over the other. And then of course we're going to learn some shortcut rules pretty soon, which will kind of make all of this seem a little bit long and tedious because those shortcut rules are pretty quick. So again, we need a point. And the point we already know is 1/2 2 from up above, and we need a slope. And actually we already know our slope as well. The slope is going to be equal to f prime at 1/2. But let's go ahead and use this definition to calculate that. F prime at 1/2 is going to be equal to the limit as h approaches 0 of f of a plus h. This is going to be f of 1/2 plus h minus f of 1/2 all over h. Okay, now we're going to actually go through and plug that in. So it's going to look at f prime of 1/2 is equal to the limit as h approaches 0, f of 1/2 plus h. Now go ahead and think about this. Let's recall our function was 1 over x. Okay, so plugging in shouldn't be so difficult when we see that. Now, that's going to be 1 over x, but everywhere I see an x, I have to put a 1/2 plus h minus f of 1/2. When I plug in a 1/2, I get a 2 out. I'm going to rewrite that as 2 over 1 all over h. Now, if I plug a 0 in here, I get 0 over 0 back. And you might want to plug it in and double check for yourself. And of course, we know 0 over 0 is indeterminate. And indeterminate means to do more work. Well, the more work we want to do is to go ahead and factor, get rid of layered fractions, hopefully cancel some stuff out. And up here I'm going to rewrite h as h over 1. And I'm going to start getting rid of these layered fractions. So in my overall denominator right here, my common denominator would be a 2, so I'm going to have 1 over 2 plus 2h over 2 minus 2 over 1 all over h. This is kind of a big layered fraction, kind of a little messier than the ones we usually look at. Limit as h approaches 0, so I'm going to rewrite this in terms of a single denominator, 1 plus 2h over 2 minus 2 over 1 all over h. Now, I've gotten this to a point, since I have that single denominator on the left-hand term, that I can flip it. So what I'm going to do is I'm going to take this denominator, 1 plus 2h all over 2, and I'm going to flip it. So when I flip that, I end up with 2 over 1 plus 2h minus 2 over 1 all over h. I'm still not making great progress here. This limit as h approaches 0. Now what I want to do is find a common denominator. Now I'm not talking about this denominator, I'm talking about up here in the overall numerator. The common denominator is going to be 1 plus 2h. Well, this first term already has 1 plus 2h for the denominator. The second term needs a 1 plus 2h multiplied by the top and bottom. I already have a 1 there times 1 plus 2h. This is all over h. Okay, when I distribute through then, I end up with f prime of x equals the limit as h approaches 0 of 2 over 1 plus 2h. Now this is where I really need to be careful. Minus 2 minus 4h, and that's all over the common denominator of 1 plus 2h. So I'm going to scoot that over just a little bit. Now the important thing here is I remember to distribute these. If I don't distribute these, the signs will be incorrect. Now when you divide by a fraction, you multiply by the reciprocal, so what ends up happening, as I have here in green, this h over 1 flips and turns into 1 over h. Rewriting again, I have f prime of x equals the limit as h approaches 0. The 2 minus 2's cancel, and I'm left with a negative 4h over 1 plus 2h, and of course this is times 1 over h. The h's cancel here. You can never cancel terms, but you can always cancel factors. And I'm left with f prime of x equals the limit as h approaches 0 of negative 4 over 1 plus 2h. And of course, as h goes to 0, 2h goes to 0, and I'm left with negative 4. This is the slope of the tangent line. Now I'm going to get the exact same equation as I did before. Remember, my point was 1/2, 2, and my slope was negative 4. So I have y minus 2 is equal to negative 4 times x minus 1/2. Y minus 2 is negative 4x plus 2. Add the 2 across, y equal negative 4x plus 4. This is my equation of the tangent line. I guess we should fill in the rest. Equation of the tangent line to the graph of f of x equals 1 over x at x equal 1/2. So the fractions there got a little bit hairy, but it was easy to keep track of once you remembered the layering effect and how we had to work with those. The last couple of things I want to talk about are the derivative of a constant and the derivative of a linear function. So let's start with the derivative of a constant. Well, a constant would be an equation like, I don't know, let's do something like y equals 7. And of course, using our functional notation, that would be f of x equals 7. Well, if we were to graph f of x equals 7, it would be this horizontal line right here, y equals 7. Well, if I want to talk about the slope of the tangent line, we can see that the tangent line is going to be the line itself. So the tangent line is going to lie right on top of this. Okay, and of course the slope of a horizontal line is 0, so the slope of the tangent line is going to be 0. So the slope of the tangent line to a constant is 0. Okay, so what does that mean? This means that f prime at any value is going to equal 0 here if f of x is a constant function, or if f of x is a constant. So the derivative of a constant is 0. This is the big takeaway. The derivative of a constant is 0. And this is going to be very important to know for Calc 1, Calc 2, Calc 3, differential equations, etc. It shows up often. The derivative of a constant is 0. The next thing I want to look at is the derivative of a linear equation or linear function. So the derivative of a linear function. Well, the one we just looked at was a line 2. It was linear as well. But this could be for any linear function. So let's say f of x is equal to 3x minus 7. Well, if we were to plot 3x minus 7, first of all, I'd have some y-intercept down here at 7, negative 7. We'll say that's negative 7. And we have a slope of 3, so we rise 3, 1, 1, run 1, etc. So this is a line y equal 3x minus 7. Now, if you think about the tangent line here, the tangent line to a line is just going to be the line itself. So the tangent line, which is in yellow, will have the same slope as the line itself. So, what does that mean? Well, that means that the slope in this case for the tangent line would be 3. So if I have f of x equals 3x minus 7, f prime at a is going to equal 3. Anywhere along this graph, the slope of the tangent line will be equal to 3. So that's another way of talking about this linear function and being able to say the tangent line for my linear function is going to be the same as the line itself. And this is really going to save us a lot of time when we start working with some of these more complicated functions to realize some of those shortcut rules. Pretty soon we're going to be learning those shortcut rules, but for the first few sections we're going to be looking at the limit definition of the derivative, and that's how we're going to be finding derivatives. Thank you.